If you've ever been in a big city like Delhi during the winter, you know exactly what I'm talking about. There's this thick, kind of grayish yellow haze that just hangs over everything. It blurs the skyline. It even makes breathing feel heavy. The air almost has a taste, right? A taste of smoke and chemicals. It's like the suffocating blanket of smog just descends on the city, and then it just stays.
So that leads to the big question, the mystery we're going to dig into. I mean, you look up, you see all this open sky, so why doesn't all that pollution just blow away? Why does this toxic soup get stuck right where we live and breathe for days, sometimes even weeks? Well, the answer isn't as simple as just blaming tailpipes in factories. It's actually a pretty fascinating and honestly a kind of frightening weather story. So let's pull back the curtain and look at the science that's literally holding an entire city hostage. Okay, so before we can figure out why things go wrong, we first have to understand how they're supposed to work. It turns out our atmosphere has this amazing built-in cleaning system. It's like a natural ventilation fan that's always running in the background. And the engine that powers this whole system? It's a simple idea called the lapse rate. Now, all that means is that normally as you go higher up, the air gets colder. That's it. And that simple fact that it gets colder the higher you go is the absolute key to how the atmosphere cleans itself. Here's a great way to think about it. Picture the whole atmosphere as one giant invisible chimney. See, the sun heats the ground, and the ground then warms up the air right above it. And what does warm air do? It rises, right? It's less dense, so it goes up, just like smoke in a chimney, and it takes all that pollution with it, carrying it up and away from us. And this isn't just some abstract idea, we've actually measured it. On an average day, for every 1,000 meters you go up, the air gets about 6.5 degrees Celsius colder. This is what's really happening out there, and scientists call it the Environmental Lapse Rate, or ELR. Just think of it as the real-world temperature change. Okay, but to know if that's a good thing for pollution, we need something to compare it to. We need a benchmark. And that's where this next number comes in. This is the rate at which a rising bubble of polluted air cools down on its own, just because it's rising and expanding. Don't worry too much about the exact numbers. What's really important here is how these two rates stack up against each other. And that comparison gives us two very different results. So look at the left. This is what we want. This is when the air around our pollution bubble is cooling down faster than the bubble itself. That means our pollution stays warmer, lighter, and just keeps on rising. The chimney is wide open and the pollution disperses. Perfect. But look at the right. This is the problem. If the surrounding air is cooling down more slowly than our bubble of pollution, that bubble quickly becomes colder and heavier than the air around it. It just stops rising, it hits a wall, and sometimes it can even sink back down. The chimney is completely blocked. But you know what? It can get even worse than just a blocked chimney. What happens when the whole system doesn't just stop working, but it actually flips upside down? Well, that's when we meet the real villain of this story, something called an inversion. It's called a temperature inversion, and it's literally the exact opposite of what's supposed to happen. Instead of the air getting colder as you go up, for a certain stretch, it actually gets warmer. Everything is completely backwards. And the effect this has is huge. A layer of warm, light air sitting on top of cold, heavy air is ridiculously stable. I mean, think about it. That cold air on the bottom has zero reason to rise up into the warmer air. So what you get is a powerful, invisible lid that gets slammed down on top of the city. Now, these inversions can happen for a few different reasons. You've got ones caused by big weather systems, you've got others that happen near the coast. But for the kind of smog we're talking about, the stuff that chokes a city like Delhi in the winter, there's one main culprit we need to focus on, and that's the radiation inversion. All right, so how does this atmospheric lid actually get created? It's a totally natural process. It happens pretty much every night. But when the conditions are just right, it creates the perfect trap. It's actually a pretty simple 4-step recipe. Okay, so step 1, the sun sets, no more heat coming in. Step 2, the ground starts losing its heat, radiating it away into space. Especially on a clear night, the ground gets cold and it gets cold fast. Step 3, that cold ground starts chilling the layer of air that's touching it through conduction. And boom, step 4, you've now got a layer of cold, dense air sitting right on the ground, trapped underneath the warmer air that's still hanging around from the daytime. The trap is officially set. And this is exactly why this whole problem is so much worse in the winter. Think about it. The nights are way longer, so the ground has more time to get really, really cold.
The skies are often clear, which lets that heat escape super efficiently. And there's usually less wind, so there's nothing to mix the air up and break that inversion layer apart. Winter is basically the perfect recipe for a really strong, long-lasting trap. Okay, so now let's connect all these dots. We're going to take all this weather science and see how it plays out in a real and frankly dangerous situation like the one on the ground in Delhi.
This quote from the source material really just nails it. The effective dispersion of pollutants depends on the degree of stability of the atmosphere. I mean, in plain English, that means the air's ability to clean itself up comes down to one thing: how stable it is. And as we've just seen, a winter inversion creates just about the most stable air you can possibly get. And this image here just shows you exactly what's happening. You have that warm inversion layer acting like a solid lid over the city. But down below, life goes on, right? You've got cars, factories, and, other sources of smoke and pollution all pumping their exhaust right into that cold layer of air at the bottom.
So what happens then? Well, the consequences are pretty grim. That inversion layer acts as a cap, so all those pollutants, they have nowhere to go. They can't go up, so they just get trapped in the very air we have to breathe. And every single day, more pollution gets added to that same trapped pocket of air. The concentration of all that toxic stuff just builds and builds and builds until the air becomes genuinely hazardous to breathe. So, after all that, what does this actually mean for us? What's the main takeaway from understanding how this atmospheric trap works? Well, here's the crucial point. Air quality isn't just about what we're pumping into the atmosphere. It's a two-part problem. It's what we emit plus the weather's ability to get rid of it. And that means we have to be extra careful, extra smart about what we release, especially at times when we know the atmosphere just can't clean itself. Look, we can't change the weather, right? We're not going to stop winter inversions from happening. They're a natural phenomenon. The one thing we can control is what we pump into the air that gets trapped underneath that lid. So really, the question this all leads to is, now that we understand the trap, what are we going to do about all the stuff we keep trapping inside it?